and let's talk about sharding. Before we start, let me quickly introduce myself. I'm a co-founder of Near Protocol, which I will briefly introduce in a second. Before Near Protocol, I was working for a company called MemSQL. And MemSQL is a sharded database. I was employee number 1 at MemSQL, and I built most of the early sharding, and then I was driving sharding when it became more mature. And before MemSQL, I was at Microsoft. That was a decade ago. We started Near Protocol around August last year, so it's one of the younger protocols, and it's a sharded blockchain. We have a huge emphasis on usability. We invest heavily into developer experience, into user experience with the blockchain, how they can onboard easier. And Near Protocol is one of the few teams that has a very strong team specifically with the industry backgrounds. We have 4 people from MemSQL. We have many ex-Googlers. We have many people who have gold medals from ACM ICPC, which is a competitive programming. And one of the key things about Near Protocol is that we are very open with the community, and so we're not behind like a walled garden. We work closely with other protocols. We work closely with the Ethereum Foundation, with Cosmos, and others. And so everything that happens in the sharding research, we share a lot of that between us. And so in this presentation, I will show you what sharding is, how sharding works, and what sort of problems still exist in sharding. So first of all, what sharding is, right? So let's say we have a blockchain. So that could be Ethereum or blockchain or Bitcoin or any blockchain. And that blockchain has some number of transactions per second it can process. So let's say it's 12. And let's say 12 is not enough. Let's say we want more. Let's say we want 36. So one thing we can do is we can run 3 blockchains. If each of them can process 12 transactions, that gives us 36. If we want to have 1,000 transactions per second, we can run 100 blockchains. And if we want to have 10,000 transactions per second, we can run 1,000 blockchains. And that's it. We solved the scalability. Problem solved. There's a small problem, there's a slight problem, which is when we have one blockchain, and there's some population of people who are willing to validate that blockchain and produce blocks. If you want to compromise the blockchain, you need to corrupt or control 51% of them. Once you have multiple blockchains, those people, when this blockchain had 12 transactions per second, there was some limitation. There was some reason why that blockchain couldn't have processed more. Maybe network was at capacity, maybe processing was at capacity, maybe storage, but there was some reason why they couldn't process more. So when we have 10 blockchains, we cannot expect all validators validate all the blockchains, because once they start validating one, they are at capacity. And that means that validators are split between them. And now if you want to corrupt one blockchain, you only need to corrupt sufficient number, 51% of the people who validated, which is, if you have 10 blockchains, that becomes 5% of people. If you have 1,000 blockchains, you need to corrupt 0.05% of all the validators, which is, that doesn't sound very hard. But that would only work if you can actually control. So let's say it's a hash power that is deciding the transaction or its stake. For you to be able to corrupt one of the chains, you either have to be able to control where your hash power goes, to which shard, or where your stake goes, or you have to be able to identify people in a particular shard and somehow corrupt them. You would either bribe them or hack them in some way. And so the most common solution to this problem is to rotate the validators. We will assign validators to shards. So let's say every shard has 100 validators. They will produce a few blocks, and then we will completely reshuffle them. And so now, first of all, I don't have control where my validation power goes, but also I cannot really corrupt someone unless I can corrupt very fast. Right? So unless I can corrupt them during the time frame while they're validating the shard, by the time I corrupt them, they already got reshuffled. And at that point, they belong to different shards. And so the idea here is that if we believe that the total population has less than 25%, let's say, malicious actors, then once we sample, let's say 100 of them, we can do some mathematical modeling and show that the number of malicious actors, the probability of having, let's say, 33% of malicious actors in the shard is very low, right? So, like let's say the full population is 10,000 and you sample 100. If you know there's 25% here at most, then the probability that you have 33% malicious actors here is very low. It can be considered to be 0. And so once that is the case, let's say this is you, and you want to know what is the latest block in the blockchain, you go to the current validators and you ask them what is the latest block. And if you hear the response from 2/3 of them, and you use some sort of BFT consensus, and that response is the same, you know that block is correct, because you know that only that 2/3 of them are actually honest. And when those validators were producing a block, they asked for it from the previous validators. And by similar reasoning, the block they got was correct block at that time. And then there's sort of induction here, and it goes all the way to the base of the induction, where the first validators, they were building on top of Genesis block, which is known to be correct. And so this blockchain, the entire blockchain is correct for as long as you make an assumption that all the validators along the way were correct, which is not a very reasonable assumption, and we'll get back to it in a second. But there's one problem, which is choosing those validators. That should be a secure computation. That computation should happen on chain. But we don't have a chain, we have multiple chains. Which chain is responsible for actually rotating the validators? And the most common solution to that problem is to have the chain, to have one blockchain to rule them all. In Ethereum, it is called the beacon chain. In Polkadot, it's called relay chain. We will be referring to it as main chain throughout the presentation. And so that chain, everybody validates it, right? So the shard chains, the validators are split among them, but the main chain, everybody validates it. And the main chain primary responsibility is to rotate the validators, assign them to shards, and do some other computations which are global to the entire system. An example of such computation, which would be very useful, is clearly the main chain has significantly higher security because everybody validates it. And so it would have been nice if we could somehow give that security from the main chain to all the shard chains. And one way to do that is for shard chains to occasionally snapshot the hash of the latest block to the beacon chain, to the main chain. If the shard chain has snapshotted their hash to the main chain and the main chain finalized the block with that snapshot, then on the shard chain later you can, in the fork choice rule, you can say, do not respect any chain that does not contain that block. And now forking anywhere before that block occurred is impossible because unless you fork the main chain, but the main chain has significantly higher security. So that is called cross-linking, and that helps you to prevent forking. But is forking the only malicious behavior that can be exercised? As a matter of fact, no. If you corrupt a shard in some way, you can fork, but you can also do another attack called invalid state transition. What invalid state transition is let's say we have a transaction in which Alice sends Bob 10 tokens, and we have the state in which Alice has 10 tokens and Bob has 0 tokens. If you get that state and apply this transaction, the state you're supposed to get is the state in which Alice has 0 tokens and Bob has 10. And so any block which applies state in this way is valid. What can happen is there could be a block produced in which in initial state Alice had 10 tokens, the transaction was applied, and now Bob has 1,000. That is an invalid state transition. And you probably often heard about forking. ETC recently had a fork. But you're unlikely to have heard about invalid state transition attacks. That is because in non-sharded blockchains, invalid state transition is impossible. The reason for that is, imagine that we actually have majority of hash power or majority of stake belonging to malicious actors, and at some point they produced an invalid block. So this block A prime contains some transaction which was applied improperly. In any modern blockchain like Ethereum or Bitcoin, all the validators are validating all the blocks, and all the users are validating all the blocks. So if you're using Bitcoin, you would be downloading the entire ledger and validating every single block. And so the moment you see the A prime, you will see it as invalid, you will discard it. And so you will not even consider B prime, C prime, or D prime as valid blocks because you know they built on top of invalid state. And so even though the honest actors built a shorter chain, every single client will know that that chain is correct. However, in a sharded blockchain, that problem does exist. And to understand why, we first need to talk a little bit about cross-shard communication. in the sharded blockchain, if we have 3 different shards, 3 different blockchains, and let's just say for now that the only kind of transactions that exist is payment transactions. Let's say I have an account on the first shard, and the person I'm sending money to has an account on the second shard. There is nobody who validates both chains. And so the transaction cannot be in the first block because then the validators cannot change the state of the second of the destination account. And the transaction cannot really be on the second chain because then the validators cannot change the state of the sender. And so what needs to happen is there's got to be some way of chains to communicate. And the way it's usually done is through this concept of receipts, where with a transaction that touches multiple shards, it originates in one of the shards. For example, in a shard in which, let's say Alice is sending money to Bob, the transaction will originate in the Alice's shard. It will debit her account. And then the validators of this shard will send some sort of receipt to the second shard with signatures confirming that the transaction was correct. And then in the second shard, the validators will verify the signatures and apply the transaction to Bob. Now, with cross-shard transactions in place, what can happen is if we manage to corrupt shard 1, I can produce completely invalid block B, in which we mint some tokens out of thin air, and then later we produce a block C, which otherwise looks correct. In block C, no transition is applied improperly. And from that block, we're sending those tokens which were minted to another shard. The second shard has no way to validate the entirety of the first shard. Right? They maybe are able to validate block C, but they cannot validate the entire history. Because if there's 1,000 shards and everybody's sending cross-shard transactions to shard 2 cannot validate all the shards. And so shard 2 has no way to know that the block was incorrect. So one way to solve that was offered is let's not allow cross-shard communication between any shards. Let's say that only some shards can communicate between each other, and every shard validates all the shards that it is neighboring, all its neighbors. Right? This way, if there's a cross-shard communication, and let's say block B was invalid, then shard 2, because shard 1 is its neighbor, validated all the blocks in the shard 1, and it knows block B is invalid. So this attack is no longer possible. And if someone wants to send money from one shard to another, which is not a neighbor, they will just send through multiple shards. And this is where the problem occurs again, right? Because, well, like corrupting shard 1 is not sufficient anymore, but now corrupting just 2 shards, which is still significantly less than full system, is sufficient. We will corrupt shard 1, produce invalid block, send a cross-shard transaction to shard 2, which is also owned by us, so we will accept the cross-shard transaction, and we will send it to shard 3. Shard 3 can only validate shard 2, but shard 2 is completely valid. There's no invalid state transition in the shard 2. So how it is solved today? Well, one way, or how it can be solved in the future, one way is you can pretend the problem does not exist. You can try to build your security in such a way that you believe, you're convinced that at no point the validator set in any shard will be corrupted. Alternatively, you can try to have some cryptographic proof that the entire blockchain is correct when you're sending a cross-shard transaction. There is such cryptographic primitives, they called snarks. But today they're not quite usable, they're very slow. Right? They're usable for private transactions, so Zcash is using them. But to prove that the entire blockchain is correct, that is not quite there yet. The long term, that will be the best solution possible. The most promising solution today is called Fisherman, where the idea is that for as long as you have at least one honest validator, that honest validator will be monitoring what is happening in other shards. And if they observe that there's some cross-shard transaction happening from the shard that they're validating, from the state that they have not observed before. So effectively, the scenario will be the shard is completely overtaken. There's more than 2/3 of malicious actors. They produce an invalid block. They never show this block to the honest validator. They produce a valid block on top of it, otherwise valid, besides the fact that it is approving an invalid block. Initiate cross-shard transaction. The honest validator will notice that this is happening, then load the blocks, identify that this block is invalid, and create some proof, some small proof that this is happening, and send this proof to the shard 2. So now at this point, shard 2 will quickly verify the proof. The proof is very lightweight, and know that the cross-shard transaction that was initiated is incorrect. The problem is that monitoring the shard, identifying this problem happened, downloading the block, validating it, it takes a lot of time. And so the challenge period, the period during which, the period that shard 2 will be waiting after cross-shard transaction was initiated before they're certain that no challenge will arrive should be pretty long. Right, so let's say both shards are producing blocks every 3 seconds. So cross-shard transaction can really, without Fisherman, be finished in like 6 seconds. With Fisherman, it needs to be on the order of minutes. So the system becomes significantly slower. But the bigger problem is that this block B, the honest validator actually needs to download the block B. The problem is that the dishonest validator might have never even published it, because in the shard 2, they cannot be downloading all the blocks from all the shards. If there's 1,000 shards, and there is 1 megabyte block produced every few seconds in every shard, you would have to download 1 gigabyte of data every few seconds. That is unfeasible. So shard 2 cannot rely on downloading this block to verify the transaction. And so this block might not even exist anywhere. Nobody besides the dishonest validators might have seen that block. And so in this case, the honest validator cannot download it, cannot validate it, cannot craft the challenge. That problem is called data availability problem. Very few protocols actually really work on this problem. Right? The only protocols that publicly say that they work on this problem, that they believe it exists, is Polkadot and Ethereum. Most of the other protocols, there's nothing in their technology which actually tries to work with data availability, or to work around the data availability problem. And the problem is that it's not only cross-shard communication that is broken, it's also snapshotting to the beacon chain. You're only snapshotting to the beacon chain the hash of the latest block. You never reveal the actual block, right? So the honest validators might not be able to download the block if the shard was corrupted, and they cannot, so the shard can completely stall. Oof. Yeah, and so there are some proposals. They mostly work around this idea of using erasure codes and providing some extra redundancy in the data that is available, and then data is somehow split. Most of those are at the very early stages, and so if you're interested in this particular topic, you can search for a paper by Vitalik called Fraud Proofs. And let me finish my presentation with a quick overview of how people actually build sharding today. Right, so Cosmos is one example of something which is very similar to sharding. Right, they have a Cosmos hub, which looks a lot like a beacon chain, and they have zones, which look a lot like shards. A few things about Cosmos is that first, validators do not rotate around zones. Validators assign to the zone, and it reduces the security a little bit. And the way Cosmos positions it is that the users of the zone have for them, it's their responsibility to identify how many validators exist there, how much they trust them, and how much they trust the zone. And in Cosmos, the cross-shard communication, cross-zone communication is carried out through a protocol called IBC, inter-blockchain communication, which allows you to move assets around between the zones, but it doesn't really allow you to do any more complex code execution. Polkadot is somewhat similar to Cosmos. However, the big difference is that the actual runtime of every blockchain is stored on the chain. So in Cosmos, every blockchain is completely different binary. In Polkadot, in principle, it can be built in such a way that the parachains are the same binaries. They don't have to be, but they could. And the runtime of the parachain is stored on-chain, meaning that validators, in principle, could rotate. However, in what Polkadot is planning to ship this year, they will not be rotating. So Polkadot will have the same security as Cosmos when they ship. And Polkadot is also using Fisherman for the security, so you don't really have to trust that. You don't need to trust that 2/3 of the validators are honest. It is enough to trust that 99%. It's enough to trust that there is at least one honest validator per shard. Zilliqa is, you probably heard of Zilliqa in the concept of sharding. Zilliqa they don't shard state, they only shard processing, meaning that every node still has to store the entire state, which is a huge limitation. And also for cross-shard transactions, they completely shut down the entire, they completely shut down sharding and process them serially. And Ethereum, Serenity, and Near, they're very similar. I'm unfortunately running out of time. But they effectively, everything I described today, this is effectively how Ethereum, Serenity, and Near work. Cool. So let me finish here. Quick thing is that we have whiteboard series where we talk to founders of different protocols. We talk to Cosmos, to Solana, where we talk a lot about technology. So check it out, near.ai/YouTube. And also next Tuesday, we're revealing our DevNet. If you're in the city, Google it. Or the link is near.ai/DevNet. Unfortunately, I don't have it on the slide. Thank you.